Hi everyone, welcome to CHM 304 and 403 Electrochemistry Workshop Lecture 2, which is on the Tafel Plot. After the lecture, I expect you to be able to make a Tafel plot. I expect you to use a Tafel plot to determine whether or not a process is anodic or cathodic. I expect you to use a Tafel plot to determine the transfer coefficient of a process. I expect you to be able to write the equation of the straight line of a Tafel plot. Here is the question. It says the following of a potential current data was obtained at 25 degrees C for a process on a platinum electrode whose surface area is 2 centimeters squared in dilute sulfuric acid. Here are the overpotential values. And here are the various current values. It says, what is the exchange current density for the process? Is the process anodic or cathodic? What is the transfer coefficient for the process if it involves the transfer of a single electron? Write an equation that describes the relationship between the current density and the overpotential. Here are the overpotential values. Here are the current values. Let alpha represent the transfer coefficient, Z number of electrons transferred, J current density, J naught exchange current density, F Faraday's constant, R gas constant in T temperature. On the basis of these symbols, we can write the forms of the Tafel equation for the anodic process as well as the cathodic process. For both equations, overpotential is the dependent variable depending on J values. So it doesn't really matter at this point the equation the plot will be based on. But just to give you a tip of an iceberg, overpotential against J for the anodic process gives a graph that has this shape. Whereas for the cathodic process, it gives a graph that has this shape. So after the plot, you'll be able to decide or know straight away which of these processes are involved for which the data was obtained by the shape of the graphs. This is the derived data of our potential values, current values. What we really need is the exchange current density, not the current itself. So we divide the various current by the area of the electrode, which is 2 centimeters squared. If we divide 5.32 by 2, it gives 2.66. We do the same thing here, it gives 12.50. We do the same thing here, there, and there. We obtain the values. Next, we take the natural logarithm of these values and obtain values to 4 decimal place. So we pick the overpotential values and the J values. Of course, we haven't done anything with the overpotential values. That is, we haven't manipulated them. There is nothing we need to do about that except to plot them subsequently. We correct these values to 1 decimal place, and that gives 1, 0, 2.5, 3.4, 4.2, and 5.0. Before we progress, this is how the graph we'll be using looks like. For some other graphs, they might be different, but basically the one we're using has a 1 centimeter squared long, which is further subdivided into 5 equal subunits, each 0.2 centimeters, such that when you put them together, you get 2 centimeters. This way 2 centimeters, that way 2 centimeters. If you stack 4 of them together, 1, 2, 3, 4, you get this. 4 centimeters this way, 4 centimeters that way, and 4 centimeters this way as well. This is the general nature of linear graphs. Let's look at them briefly before we progress. These are equations of the straight line of a linear graph. The first one has y equal to mx minus c. Y is the dependent variable depending on values of x. Yx is the independent variable. At this point on the y-axis, x is equal to 0. So we substitute 0 there, and we obtain an expression for y equal to negative c. That's why the intercept here is 0. Is rather as negative c, so to say. If we substitute at this point, y is 0. So if we substitute 0 there and rearrange and make x the subject of the formula, we obtain c all over m as the intercept at that point. The gradient, which is m, is obtained by taking the change in y and dividing it by the change in x. If, for instance, this graph had passed first of all at the y-axis before the x-axis, the intercept there would be c, where that on the x-axis would be negative m all over c. And this is the equation of the straight line. Next, this graph, y equal to mx, passes through the origin, so it has no intercept. The gradient is change in y all over change in x. For these three lines, the values of y increase with increase in x. If you compare this, where the values of y decrease with increase in x, you obtain a negative gradient. Here you have x equal to 0, and because x is equal to 0, you substitute 0 there, and the whole of this expression becomes y equal to c. That's why we've got c there. At this point, y is equal to 0. We substitute 0 there, rearrange, make x the subject of the formula. We obtain c all over m as the point there. We take the gradient, change in y, substitute there, change in x, we substitute it there, and we obtain a negative gradient. Yeah, so this is our graph. This is what we've got to make our plot on. Basically, the data we are plotting its over potential against lane J values. We draw our lines first of all. We label the axis. We know that the maximum value on the vertical axis, which is the over potential axis, is 250, where the minimum is 50 millivolts. So how do we decide the scale for this graph? We take the difference between 250 and 50, we obtain 200. We divide by the grid space, the 1 centimeter square boxes. We've got 1, 2, 3, 4, 5, 6. We've got 6 of them. So we divide 200 by 6. We obtain something in the region of 33. So 33 is what we actually have. If you place 33 at this point, we'll be able to cover that range. But it's quite difficult to place 33 and divide it quite equally between these spaces. So we multiply it by 2. That gives 66. So But the same thing applies to 66. It's difficult to divide it into equal units quite conveniently on the graph grids. So we check values in between 33 and 66 and choose. And one quick value to consider is 50. So if we place 50 at this point, 50, 100 there, 150 there, 200, 250 there, and 300 there, we're able to maximize the grid space of the graph while also encapsulating the values for the minimum as well as the maximum. So this is what we have. We apply the same principle on the horizontal axis, and we obtain this. We write our scale up there boldly. We make our first point plot. Place our first points, 50 against 1, 100 against 2.5, 150 against 3.4, 200 against 4.2, and 250 against 5. Draw a straight line. Obviously, you can see that the point at 50 is off the line. If you recall from our lecture where we were deriving the equation of the Tafel plot, we said we assumed that the overpotential values were greater than 100 millivolts. So that's why at values less than 100 millivolts, there is this deviation from the linear plot. Yeah, so we choose 2 points on the grid space that intercept quite properly, and draw a rectangle through to note them. The change in x, we've got 2 there, we've got 5.6 there. On the vertical axis, we've got 290 there, so to say, and we've got 60 this way. Now, the first question says, what is the exchange current density for the process? Let us return to our graph. If you look at this graph, it takes this form, and the equation that applies is this. That is to say that the process is anodic. And if you compare this to this graph, which we looked at previously, you will notice that this is the gradient, and that is the intercept. Now, at this point, where the intercept is, that's on the y-axis, the overpotential is 0. So we substitute 0 in this equation. In rearrange, we'll obtain this expression. We cancel them, and we are left with ln J equal to ln J naught. Therefore, the intercept on the ln J axis is 1, and ln J naught is equal to 1, so to say. We take the exponential of both sides, and we obtain 2.72 milliamperes per centimeter squared. The next question says, is the process anodic or cathodic? We can't answer that question unless we solve the slope. Changing over potential all over changing ln J. We substitute the values we had here for the horizontal axis, and then here for the vertical axis, and it gives us 63.9 millivolts. Again, because the gradient is positive, it means the process is anodic. Next, It says, what is the transfer coefficient for the process if it involves the transfer of a single electron? Because the process is anodic, the Tafel equation that applies is this one. And that is M, that is C. If we write the equation in terms of M and C, we have this. That is, M is equal to this and C is equal to this. So, to obtain the transfer coefficient, this is the term that has the transfer coefficient, as well as this. Whereas we know this, but we don't know this, and we can find this from the gradient of the plot. So the gradient is equal to this. All we are left with is to substitute values for the gas constant, which is R, the temperature, which is 298, and the number of electrons that have been transferred, which is actually 1, and F, the Faraday's constant. When we do that, we are left with an expression. This expression is equal to this if it's evaluated. We rearrange this expression based on what we have, 1 minus alpha equal to this. We obtain alpha as 0.6. The next question says, write an equation that describes the relationship between the current density and the overpotential. What the question actually wants is for us to write an equation that describes this relationship between the overpotential and ln J. To do that, we need information about the slope, which we have here, and we need information about the intercept. And we know that the intercept is product of this times ln J naught. So we write our equation of the straight line on that basis, bearing in mind that this is M, the gradient, that is C, the intercept, and M is equal to this, and C is equal to the product of the gradient times ln J. So this is the gradient, and ln J naught gives this value. Thanks for watching. I've left links to the PDF version of this workshop, plus study questions, and there is a journal article that discusses how the Tafel equation is used in corrosion studies. Thank you once again for watching. I'll be producing other videos for physical chemistry questions.